Hello and welcome to today's introductory webinar on data analysis with MATLAB for Excel users. My name is Adam Fillion and I'm an application engineer with the MathWorks. The first thing I would like to do today is give you all a sneak peek of the end product. What is it that we're working towards? So what I'm going to do now is I'm going to tab over to an HTML report that I have. And this is a report that documents the type of work that we're going to be doing in MATLAB today. So as I scroll through, you can see we have title explaining what are we doing in this report. We have things like hyperlink table of contents, different sections with comments explaining what's going on. You can see the MATLAB code as well as any outputs that it's producing, along with things like algebraic equations. And this is a report that we generated from MATLAB with one click of a button. So this is going to be our end goal for today. We eventually want to get to the point where we can click one button and go straight from data living inside of an Excel file, bring it into MATLAB, analyze it, and then automatically document the work that we did in a portable, readable report similar to what you see right now. So that's what we're working towards. Before we dive into that, I do want to step back to the slides for just a moment and set the stage for the rest of today's presentation. Now, regardless of whether you're working in Excel or MATLAB or really any other platform, we find that everyone follows pretty much the same workflow whenever they want to analyze some data. So we're going to lay this out here today just to get everyone on common terms. So we think of this as three distinct phases, and the first phase is what we like to call the access phase. And the whole point of this is to just get your data from wherever it's living into your environment so you can start working with it. So today we'll take a look at bringing Excel files into MATLAB, but your data could be coming from almost anywhere. It could be coming from text files or binary files or multimedia files. It could be coming from databases or streaming off the web. We can also hook MATLAB directly up into a wide variety of hardware, so we can stream data in directly from testing equipment into MATLAB. But really we want to get through this phase as quickly as possible so we can get to what we like to call explore and discover. Now, this is where you want to be spending the majority of your time. This is where all the really interesting things happen, where you're plotting your data, analyzing it, modeling it, building up algorithms around it, maybe putting a nice user interface in the front of your work. But you can do all the analysis you want. It's not really worth anything. It's not really valuable until you share what you've done with other people. And so that's the last phase here, is how can we take the work that we've done and share it with different people in different formats. So you already saw one example with an HTML report. We can create reports in many other formats as well. We can also hook MATLAB directly into other downstream design tools, and we can even deploy functionality that we've built in MATLAB and give it to other people so that they can use it without needing MATLAB on their machine. Now, we've laid this out in a bit of a linear fashion here, but if you've ever done this kind of work before, I'm sure you've already realized you will almost never go through this process and get everything right the first time. You're going to need to import many different files with different data. You're going to need to plot things in many different ways. Some of those plots might be really useful and you want to keep them and reuse them. Some of them, maybe not, and you can get rid of them. You'll need to go through many different iterations of your algorithm to get it working right and share the results with many different people in different formats. So one of the keys we'll be looking at today is how can we use MATLAB to automate this process? How can we do it sort of the easy way once in MATLAB and then have MATLAB help us automate this process so we can very easily do it repeatedly over and over again. So as we work through today's demonstration, I really want you to keep this workflow in mind and also pay close attention to the tools that we use in MATLAB and some of the tips and tricks that we talk about, and really think about how all of this might be applied to the work that you're doing. Now, the demonstration that we'll be working through is on modeling global solar radiation, so on how much of the sun's radiation is actually hitting the Earth's surface. Now, this is an important problem in many areas. One of those areas is in designing photovoltaic systems, so solar-powered systems. In order to properly design our system, we need to know how much electricity will we get from our solar cells. In order to know that, we need to know how much solar radiation can we expect. However, solar radiation is not the easiest thing to directly measure. That means that there are many parts of the world, like developing countries, where there is not a history of solar radiation measurements at that location. So if we're going to properly design our system, we need to be able to find some way to predict what will the solar radiation measurements be there, so we can then predict how much electricity will we get, and we can properly design our system. Now, there are many different ways we could model solar radiation. For today, we picked this equation you see over here. I don't want you to worry about it too much. We got this from a journal article on this topic, and we picked this particular way of modeling it because it meets our criteria of using low-cost, readily available inputs that we could get basically anywhere in the world. So this model takes as inputs H, the average relative humidity for the day, and delta T, the maximum daily change in temperature, and gives us back the solar ratio. So the workflow we're going to go through today is we have some real-world data from a weather station in Davis, California, where they measured H, delta T, and they had some fancy equipment that actually allowed them to measure the solar ratio. So we're going to plug in the values for RS, H, and delta T, and we're going to fit this model. We're going to get estimates for those four coefficients you see, A, B, C, and N, because if we can get good estimates for those coefficients, then we can take this model in for any new H and delta T. We can get a prediction for the solar ratio, so we can then predict how much electricity we'll get from our solar cells and properly design our system. So that's, from a high level, the idea of what we're going to be doing today, but that's certainly enough PowerPoint. Let's go ahead and hop over to MATLAB. Okay, so for those of you who haven't seen it before, this is the MATLAB desktop. I'm using the R2013B release of MATLAB. We have two releases a year, an A release in the spring, a B release in the fall, so this is the fall 2013 release. We've got a number of windows and options going on here. I'll explain each of these as they become relevant. As we'll see today, there's a number of different ways we could interact with and use MATLAB. One of the common ways is using what we call the command window, which I've positioned over here on the right. Now, this is an interactive environment. We could use it sort of like a big graphing calculator if we wanted to. Just enter some simple commands, get the results back immediately. But we can also store results inside of named containers, what we call variables. So here I'm just telling MATLAB I want you to take the value of 5 and store it in a container and call it A. And then if I want to use that, well, I can simply tell MATLAB, take whatever's inside of A, and you can think of it as almost copy-pasting the results right here. Multiply it by 7, and then store that result in another container called B. So for those of you coming from a background of Excel, you can already start to see some of the big differences between working in Excel and working in MATLAB. Excel is very focused on locations. Data lives in a particular location inside of a spreadsheet. When we want to enter a formula to do some analysis, we need to enter that formula in an empty location inside of our spreadsheet, and all the inputs reference different locations where those inputs live. Here inside of MATLAB, we don't focus on locations. Instead, we use these named containers, these variables, to store our data and reference it. Now, one of the big differences between MATLAB and a lot of other programming languages out there is the way in which it understands data, the way in which it thinks about it. MATLAB actually thinks of all data as matrices. And if you're not familiar with a matrix, you can think of it just as a spreadsheet of values. So it could be a row, it could be a column, it could be a two-dimensional or higher dimensional matrix, even a single value like 5 here or a value like pi. MATLAB actually thinks of that as a one-by-one matrix of values. It's actually where MATLAB gets its name. It stands for Matrix Laboratory. So if I want to create a row of numbers in MATLAB, I can do that very easily by putting them inside of square brackets and separating them with commas. So here I just created a row, 1, 2, 3. And now if I want to perform some operation on every value inside of this variable C, let's say I want to take the sign of it, well, I can enter in the sign command, open the parentheses to start giving it inputs. What do I want to input to it? The variable C. And then close my parentheses and hit enter. And this will perform that operation on every number inside of C and return the value in the corresponding location in the answer. Now, you don't need to know matrix math or matrix algebra in order to use MATLAB and be successful with it. But if you do, it's really the ideal environment for it. So if I want to take the transpose of C, if I want to turn it from a row into a column, I can do that very easily and store that inside of D. And then I can say C times D or D times C, and that'll get me either a scalar or a 2D matrix depending on my order of operations. So that's the command window. It's a very easy interactive environment, and we'll be coming back to it a number of times today. The only other area of MATLAB I want to point out right now was what I have positioned in the bottom left called the workspace, and I'll double click to expand this out. Now you can think of the workspace as MATLAB's memory. This is where MATLAB shows all the different variables that it has in memory and it knows about. And you can also see some basic information here. And if I right click on this gray area, you can also see some basic statistics that we can add. Things like the min and the max, the mean, the standard deviation. So at any moment we could just take a quick glance at our workspace and see what data do we have and get some basic information about it. So for now, I'm going to go ahead and collapse this workspace back down by double clicking, and then come up to my Home tab. Now this tab interface in MATLAB was new in the 2012 B release, so if you're on an older version of MATLAB, this may look a little bit different. And we made this change to the desktop for reasons of discoverability. What we had found is our developers had spent a lot of time and effort over the years putting a lot of different tools into MATLAB to help you get your work done, but most people had no idea they were there because it was buried behind the old menu system. So we tried to bring it out to the front today with this tab interface. And we'll be coming to it a number of times today. For now, I'm simply going to clear my workspace and clear my commands. Now we're back where we started. So if we think about that data analysis workflow that we talked about earlier, the first step is access. We need to get our data from where it's living in Excel into our MATLAB environment so we can start working with it. So up here in the top left, I have a current folder browser. Just shows me what's MATLAB's current working directory. And you see in here I have this file davisdaily.xlsx, and I'll right-click and open this outside of MATLAB. So here you can see the raw data file coming to us from Davis, California. So you have some information on the station, some timestamping information. You see this starts January 1st, 2001, and goes through December 31st, 2010. So we have 10 years worth of data. And as I scroll to the right, you see we have a number of atmospheric measurements. So our first step is we need to get this data from inside of Excel into MATLAB. But as I find is often the case, there's actually a lot more information here than we actually need. So how can we not just get this data in, but get in just the data that we actually care about? Now, anytime you want to do something inside of MATLAB, there's always a way that we could write some code in order to do it. But today I'm going to focus on how can we do it the easy way. So up here in my Home tab, I have this big Import Data button. This opens up a directory browser, lets me go pick out a data file, and opens it up inside of what we call the Import tool. Now, the Import tool is a great tool for importing data from different types of files, particularly if you want to set up customizations on the import process. So you see some tabs up top. Tabs are always designed to work from left to right. So we could start off by maybe specifying the range or a row of inside the Excel file we automatically want to grab names from. And then what type of format do we want to read this data in as? Do we want to read the whole thing in as one big matrix? Or maybe we instead import every column inside of our Excel file as a different variable in our MATLAB workspace. So I can come down here and I can actually interactively select which parts do I want. So here I'm going to click on my date column and then control click on day of the year, solar ratio. And this doesn't have the change in temperature that I need for my formula, but it has the max and the min, and we can compute it from that. And if I scroll over a bit, we can see the average relative humidity that we need. We can also grab the borders here and just drag these around. There's a number of other customizations that we could set up, but let's say this is good enough for now. I'll click this check mark. And now you see back here in the workspace, I have 6 variables named according to their 6 columns inside of Excel. And you can see their size, 3652 by 1, so row 3,652 rows by 1 column. And so that's all it took to read that data in from Excel. So as you can see, the import tool is a great way to very easily and very quickly read in data from different types of files into the MATLAB environment. Okay, so now we got our data in. That was our access phase. So now we need to start thinking about, well, what are we going to do with our data? You might have your own particular favorite thing to do when you first get your hands on some new data. For me, I always like to plot things, and I like to generate a lot of different plots so I can look at our data in different ways and try to understand what's going on inside of it. So again, we could always write some commands inside of MATLAB in order to do that. But instead, I'm going to come down to my workspace, and here I can select any series of variables I want to visualize. Let's say I want to start with my solar ratio that I'm trying to predict. And now I can go up to my Plots tab. And here I can see what I picked out of my workspace and then a series of icons. And if I expand this out, MATLAB has actually already sorted through all the different built-in visualizations it has at its disposal that can accept the data I selected in my workspace as an input. So this is all the different ways MATLAB could visualize a single column of numbers. So this Plots tab is a great way to learn about new visual filters we could apply to our data to try to learn about what's going on inside of it and very quickly generate a lot of them. So let's say I want to start off with just the most basic, simplest plot that there is in MATLAB, the simple line plot. So I can click on Plot up here, and there we go. So this is a simple line plot in MATLAB, and it's not a static plot. I can very easily grab my magnifying glass and zoom in and pan around and start trying to figure out what's going on inside of my data. Maybe grab my data cursor and take a look at, well, what are the particular values at each of these points. And if I zoom back out, you may notice, well, it looks like maybe there's a little bit of periodicity here in our data. But as it is, I actually don't find this particular plot to be too useful because I don't know what solar ratio values should look like. I don't work with them too much. And this is actually one of the reasons why I really like using the Plots tab. It didn't cost me anything to create this. I didn't need to go looking for commands. So if I create a plot it's not too useful, no big deal. Let's close it down and try something else. Maybe like a histogram. Okay, so I find this to be a bit more useful. This shows me that I have some amount of data pretty much throughout the entire range from 0 to 1, but most of it is concentrated between around 0.6 to 0.8. So we can keep exploring this further if we like, trying more plots and different kinds of plots, and I really encourage you all to use the Plots tab regularly. It's a great way to very quickly generate lots of different figures and different ways to look at your data. You may also notice that down here in the command window, we get a couple of commands printed out. So you can see that whenever I clicked on one of these icons up here, what MATLAB actually did is it figured out, okay, what kind of command do I need to generate that plot with the piece of data picked from the workspace, and then printed it to the command window and executed it so that if I like it, I don't have to go hunting for it. So we just did some fairly quick plots there using the Plots tab, but let's say at this point I want to dive into it even further. So in that first line plot you saw, it looked like maybe there's some periodicity in our data. Maybe I want to explore that in more detail with a more complex plot. So let's say now maybe I want to put the day of the year on the x-axis, the actual year the measurement was taken on the y-axis, and then my solar ratio value on the z-axis, so make a 3D plot. But before I can do that, you may notice that down here in my workspace, I don't have a variable that tells me what is the year at every particular point. I have the day of the year and I have the full date, but I don't have just the year. So I need to figure out what kind of command could I use in MATLAB to strip out just the year at every measurement. Now, this can oftentimes be one of the hardest parts of learning any new language or even using an environment that you're already familiar with. Now in MATLAB, we've built searching for new functionality and new ideas directly into the desktop up here in the top right. So I can type in anything I want to learn more about. Let's say I want to learn more about dates inside of MATLAB. And if I hit enter, I can do a full search of MATLAB's documentation, but it'll actually also give me just a quick pop-up of what are some related functions and some search terms that it thinks might be good to search for. So we could do a full documentation search, but oftentimes you'll find something pretty useful just right here in this little pop-up. And in this particular case, we can see that it's suggested a command called datevec. See brief description, convert date and time to a vector of its components. Sounds kind of interesting. If we click on this, this will take us directly to its documentation page. Now I know there's a lot of software applications out where the help documentation isn't actually that helpful. I think MATLAB's help documentation is fantastic. I hope all of you will use it regularly. I certainly do. I've been using MATLAB for almost 10 years now. I still go to the documentation anytime that there's something about MATLAB where I want to learn more. Now every command in MATLAB has a documentation page with the same format, so once you learn to read the format, it's very easy to find any new information you want about any new command you come across. CC title over the top, brief description, syntax, so different ways we can use it with different optional inputs, detailed descriptions of all those different formats. And down here you can see a particular one that returns the components of the date as the year, month, day, hour, minute, and second. So it splits it up into these 6 components. So this sounds pretty good. This would allow me to take my full date and split it up into these components so I can just grab the year. And if I want to see an example of this particular method, click on example over here. And this will take you down to my favorite section of the documentation, the examples. So every command has examples to go along with it, and not just show you how to use it, but also what's the output that you should expect from that particular form of it. Okay, so here using the documentation, we found our datevec command that we'd use to get out just the year. Now we're ready to use it. So anytime I want to use a command in MATLAB and I want to call it from here in the command window, it has the same sort of format. So the first thing I do is I list any outputs. What are new variables that I want to have pop up down here in the workspace as a result of this command? If there are multiple ones, we list them inside of square brackets and separate them by commas. So the first one I'm going to get back from this command is the year, but then I actually don't care about what is the month, day, hour, minute, and second at each of these points. So rather than creating dummy variables to hold this data that I don't need, I'm going to use the tilde operator to tell MATLAB, I actually don't care what these values are, don't bother giving them back to me. So we list our outputs first, equals the name of the function, datevec, and then we open up parentheses to start listing the inputs. What are we going to pass to this function? And if I open the parentheses and leave my cursor there for a second, MATLAB will actually pop up with a quick summary of what are some of the different ways I could use it, and if we want more information, we can click on more help down here and go straight back to the documentation page. So what am I going to put in here? I'm going to put in my date1 variable, which I can either type out or I could actually just select it in the workspace and drag and drop. Then close our parentheses. And then notice here I'm going to put a semicolon at the end. If I don't do that, MATLAB interprets that as telling it that I want MATLAB to print out all the results to the command window. That can be really useful if I'm quickly prototyping and working with small data. But here I have over 3,000 rows. MATLAB would print all that out. I don't want to do that, so I use the semicolon to suppress it. We hit enter, And there we go. And now down here in my workspace, you can see we now have this year variable, which is the same size as the date. And now it'll tell me just what's the year. Okay, so now we're ready to go. So now I can select my day of the year variable first. That'll put it on the x-axis. And then control click on year and then solar ratio. Up here in my plots tab, you can see what I've selected. The order in which I click on the variables is the order in which MATLAB will use them. And then you see a new selection of plots up here. So MATLAB, again, is dynamically searching for what are all the different ways that I could visualize the data that's been selected. So in this case, visualize 3 different columns of data. In this case, let's say we want to try a scatter 3 plot. Okay, so this might give us a good baseline to work from. The plots tab, when it's doing all these different plots, it's using all the default settings. But by default, the scatter plot here, it's a little hard to read. It's sort of a big blob. So what I'd like to do is I'd like to be able to customize this to make it more readable and more useful to me. Again, we could always write some code in MATLAB in order to do that. Or we can come up here and use this little guy, this little button up here in the top right. So when I click on this, this opens up what we call the plot tools. So this is an interactive environment where I can make pretty much any customization that I would want to graphics in MATLAB. We start over here on the right with the plot browser, and I can pick out different objects inside of my plot. So let's say I want to start with my data. Then we come down here to the bottom to the property editor. This shows us all the most commonly edited properties. And we might want to change the marker from a big circle, maybe down to a little dot. That makes it less of a big blob. But what I'd really like to do is I'd like to give this a sense of depth. So the way I'm going to do that is rather than coloring each point by this monochromatic blue, I'm going to have each point be colored relative to its value in a variable from my workspace. So I'm going to come down here to color, and I'm going to color each point according to its value in solar ratio, according to its Z value. We'll select that, refresh our data, and there we go. And now you can see each point is colored according to its Z value. Makes it much easier to tell when I'm looking at a particular point, where is it in the 3D space? Is it high in the Z on the Z axis, or is it further down? And if I want to see, well, what values do these colors associate with? Well, up here in our toolbar, we have a number of useful tools. One of them allows us to insert a color bar so we can see which colors map to which values of the solar ratio. So the property editor allows us access to the most commonly edited properties. If we click on this More Properties button over here, this actually opens up what we call the Property Inspector, and this allows us to interactively modify literally every single modifiable property about graphics in MATLAB. So we can very easily and interactively make every customization that we would want to through this interface. So there we just modified our data. Let's say we want to modify our axes as well. So here I'll add in some labels. Maybe let's call this day of the year. Y-axis, this is the year. Z-axis, this is the solar ratio. And we could modify additional things as well, like the tick marks, what's the font. Axes have their own set of additional properties we can modify. Maybe we want to click on the background and modify the larger figure window as well. Maybe change the color map, which is the colors that are being plotted, or change the background from gray to white. Personally, I prefer a white background, just a personal preference. And over here on the left, we also have the figure palette. This allows us to do a bit more advanced maneuvers like creating subplots, so additional axes inside of the same figure window. I can just draw out what I want that orientation of axes to look like. Or maybe do something like adding in some annotations. But eventually we'll get our plot working just the way that we like. Let's say this is good enough for our purposes today. And we can come up here and close down the plot tools. So now we've got this nice, readable custom plot that we were able to very easily create with our plot tools. So now I'm going to come up to my toolbar, grab my Rotate 3D tool, and if I left click and drag, we can actually rotate this around and look at it in 3D. If I right click, we can jump to a particular view like XZ. So now we're looking at solar ratio versus our day of the year. Now we can actually see a little bit of a pattern emerging here. So in the middle of the year, looks like our solar ratio values are pretty consistently high. When we get into the winter months at the end and beginning of the year, we see a much higher variance inside of our data. So if you're familiar at all with Davis, California, this shouldn't surprise you too much. During the summer months, it's pretty consistently sunny every day. As you get into the winter, that's more of the rainy season. You get a lot more cloud coverage, which means a lot less sunlight hitting the surface. So using the plot tab, that gave us a good starting point. And then using the plot tools, we were able to very easily and interactively build up this custom plot. But then if I wasn't careful and I came up here and I hit this red X up here, this would actually close this plot down, and then I would need to go back through that interactive process to recreate it. So rather than doing that, I'm going to come up here to the File menu inside of the Figure window and go to Generate Code. And what MATLAB will do is it will automatically generate all the code I need, put inside of a command that I can then use to recreate this custom visualization with any new set of data. Now, you see this opened up inside of what we call the MATLAB editor window for editing MATLAB files. You may notice we got some new tabs up top as well. These dark blue tabs on the left, these are global. They're always there. The lighter blue ones on the right are contextual. They pop up as we need them. So here inside of my editor tab, I can go ahead and save this. Let's call it Create Figure 1. And now if I tab back over to my plot, let me close this down so we know we're starting fresh. Now I can use this command to recreate that plot with a new set of data. So I can call create figure 1, open up the parentheses, and then give it the X data, which is my day of the year. Y data is the year. So ratio is our Z data. So you see X, Y, Z up here. Then you see this value S. S is actually what is the size of the markers inside of the figure. In this particular case, I actually don't want to specify it. I want MATLAB to go use the default. So with these types of optional inputs, if I want MATLAB to use the default, oftentimes what I can do is give it this empty set of brackets, an empty matrix, and when MATLAB sees that, that tells MATLAB nothing was specified, go use the default. And then lastly, what do I want to color it by? I want to color it according to its solar ratio. Hit enter, and now we get our same custom plot back. So this is a fantastic tool for automating this process where I can interactively set up all these customizations using the plot tools and then generate the code that will recreate it, reapply these rules to any new set of data. And this is not tied to the data that we used to create it. So let's say I want to plot things a little bit differently. I'm going to hit the up arrow here to bring up my previous command. And let's say rather than coloring according to its Z value, I want to color each point according to its value in a fourth variable. So let's say I want to plot the same XYZ points, but now I want to color every point according to the average relative humidity. So now we see something a little bit different. And if we go back to that XZ view that we saw earlier, now we get some additional information. So now we can see here in the middle of the year, when solar ratio values are pretty consistently high, we can see the average relative humidity is pretty consistently low. As we get into the winter months, when the variance in the solar ratio gets much higher, we can see that also happens when we get much higher average relative humidity. So again, this is a great way where we can set up all these custom rules for how to visualize data and apply it to any new data set that we come across. So generating this code is a great tool for automation. I find it can also be a great tool for learning. So if we scroll down in this file, you can actually see comments, this green code just explaining what's going on, and then some commands. So here's how we label the X and Y axes. And here's how MATLAB modified the scatter3 plot that we originally saw back here from the Plots tab in order to get it the way that we like. So this can be a great tool for learning how to programmatically do new plotting routines inside of MATLAB. Personally, if I need to know what's the programmatic way to do some complex custom visualization in MATLAB and I don't know it offhand, we could look through the documentation to figure that out. What I'll do is I will plot some data, open up the plot tools, do all the customizations interactively, get it to the point where it's exactly the way that I want it, and then go to File, Generate Code, and MATLAB will give me all the code that I need to programmatically recreate that custom behavior with any new set of data. So this is a really fantastic tool. I hope all of you will make very good use of it when you're working at MATLAB. Okay, so at this point, we've been exploring our data a bit, we've been plotting it in different ways, and let's say at this point we realize we actually need some additional information in order to complete this analysis. Maybe there was some information back in that original spreadsheet that we forgot to import, or maybe we have additional spreadsheets. So I have the spreadsheet over here for information from Davis, but if I also have information from other weather stations throughout California. Well, if we go back to our import tool, we could go through and pick out some additional columns to import, or maybe open this up for additional files. But as we continue to import more and more variables into our workspace, it can get confusing and maybe difficult to manage, especially for importing from multiple files at the same time where they all have the same names across all of these different columns. So what I'm going to introduce now is a new data type inside of MATLAB that can help us manage all of this data. And it's called a table. So you can think of a table as, in one way, just a tool to help us organize and manage our data. So inside of our workspace, it will give us just one variable. We can name that here. So let's say we want to call it Solar Davis. And then inside of that table, that's where each of these columns we've selected inside of Excel will live. So this can be very, very useful for helping us manage more complex data sets. So now if I want to read in this data from Davis, and then I want to read in the same file from a different weather station in Southern California that has the same columns, the same names, I can read that into a different table, and it's much easier to manage. Now there's an additional problem we actually haven't thought about yet, which is what do we want to do if there is some missing information inside of this Excel sheet? So if I scroll down a bit, you'll notice that down here on May 20th of 2001, we actually don't have a measurement for what was the minimum air temperature that day. Nobody recorded it. So what do we want to do when there's a blank inside of Excel? Well, we could set some rules up here. By default, it will replace any unimportable cells with what's called a nan, not a number. But then we still need to do something about it inside of MATLAB. So you may have your own favorite way of handling this missing data. Some people like to fit maybe a smoothing spline to it so we can get an estimate for what might that value have been. But for today, what we're going to do is we're going to take any observation, any row where we're missing any data, and we just want to completely remove it from our set of data so it does not become a part of our model. In order to do that, I'm just going to come up here inside my import tool and decide to exclude rows with unimportable cells. You notice the color is purple. And down here you see this row turns purple, which means that when we're done with the import process, this row will now be excluded from our data. So we can very easily exclude anything that has any missing values or otherwise importable cells from Excel just right here in this interface. So now I could come up here and click on this check mark, but you may have noticed we actually haven't automated the access phase yet. So we have this little drop-down menu down here that gives us a couple of options. We can either import the data, or we can generate either a script or a function to get all the code that will programmatically automate this process for us. And here I'll go ahead and generate a function. So you know this just generates what's called a function file. So functions all start with the same format. You see the keyword function here. And functions then list any outputs, equals, the name of the function, and then any inputs inside of parentheses. Now functions are really useful. You can think of them sort of as a way to modularize your analysis. What goes on inside of the function has no idea about the outside world, about this workspace back here, except what you pass in as inputs. Likewise, the outside world has no idea about what happens inside of this function except what you pass back out as an output. So here we can save this function file. Let's call it import file 1. And now if I clear my workspace in my commands, I'll do that programmatically here using clear and CLC. Now we can use this command that the import tool just automatically generated for us to automate the process of reading in this data. So the output is going to be a table. Maybe I want to call this Solar Davis, equals the name of the function, import file 1. And then inside of parentheses, I can give it some inputs. In this case, I'm just going to specify one, just what is the name of the file, davisdaily.xlsx. And notice here that I'm using the single quotes and it turns purple. That just tells MATLAB that this is literal text. It's not the name of a function, it's not the name of a variable that contains something else inside of it, it's just literal text for it to use. Hit enter. And MATLAB will then run through all the code inside of this function file to automatically import this data into our workspace. So you can see now the import tool gave us all the code that we need to automate the access phase, and now I can just give it any file name that meets that same format, and it'll automatically import it into a new table that I can name whatever I want. So again, this is a great tool for automating this process. Similar to the code we got from the plot tools, this can also be used for learning. So if I scroll down a bit, you can see some comments and also the code that we're using. So here inside of this function, you can see this green text is just comments explaining what's going on, and you see a couple calls to this function xlsread. So if you ever see a function in MATLAB, you're not sure what it does, you want more information, right-click on it and go to Help on Selection. And this will take you right to its documentation page. So here we can see this is a function for reading data from a Microsoft Excel spreadsheet file. So this is the programmatic way to read data from Excel into MATLAB. If you scroll all the way down to the bottom of this page, you see an additional section called See Also with related functions. One of them is xlswrite. So this is a programmatic way to write data back out to a Microsoft Excel spreadsheet file. So again, this generating code can be very useful for automation and also useful for learning. But one of the nice things about it also is that we actually don't need to understand how this code works. So MATLAB just gave us all the code, and if we want, we can just close this down and just use it as is. Now notice back here in my workspace, I now just have one variable in here called Solar Davis, and you see the size. It now has fewer rows, so we actually removed a number of rows that had missing data. And you see 6 columns. Now if I double click on any variable down here in the workspace, it'll open it up in what we call the variable editor, where we can interactively examine and modify any value. And here you see the different columns from Excel residing inside of our table. And I can use the fields inside of the table the same way that I would use a lot of other variables. So if I just select this column here for solar ratio, I can go back to my plots tab, and here you can see the selection, so how it's referencing it, the name of the table dot the name of the column. And then I can select any one of these visualizations like the histogram command. We get the same histogram back, and down here you can see the programmatic way for doing that. So the name of the table dot name of the column. So there are a lot of really great reasons to use tables. Tables are a great way to manage your data, particularly if you have data of different types. So we kept things fairly simple for today because it's just an hour-long introductory session, but we could also be mixing in with our numbers many other data types, so mixing in text inside of this table. And tables also have many nice functions associated with them for managing messy data sets and for ordering your data. So finding intersections or unions between different data sets and sorting them and stacking them in different ways and joining different data sets together so that everything lines up right based on a particular set of criteria or different variables. Unfortunately, since we don't have a lot of time today, we don't have the time to dive into all of these niceties for using tables to sort and manage your data. But I did want to make sure everybody was aware of them because tables can be very useful, and they are brand new in the 2013B release. Okay, so now we've automated the access phase, and now we've brought our data in as a table. And let's say I want to get back to exactly where I was, but now using the table data. Well, I could try to remember all the commands that I used, but I could also go back to my command history by using the up arrow. And actually, if I start typing out a command, for example, if I put in a square bracket here and I hit up, MATLAB will actually go back to through the previous commands that began with the same set of characters. So here I can see the command where I created the year. So now all I need to do this for my table data is to instead use solardavis.date. So here I can start typing out the name of the table, and then if I hit tab, MATLAB will try to auto-complete it for me. Then dot, and if I hit tab again, MATLAB will tell me what are all the things that could go after the dot. So here I'll go ahead and pick the date. And now we see we get the same year variable back here in our workspace. Now if I start typing out that create figure function, hit up, this will bring out the previous command that I used. And now really all I need to do is copy paste this solar Davis dot in front of the appropriate variables like average relative humidity, solar ratio, and day of the year. Note that I also could put solar Davis dot in front of the year variable up here. That would have added it as another column inside of my table. I just chose not to do that in this case. And there we go, and now we got the same custom plot back. Okay, so now we've gone through, we've automated the process of accessing our data. We use the import tool to set up those customizations interactively and then automatically generate the code. We use the plots tab to do some quick visualizations on our data. We're able to use the MATLAB documentation to help us figure out how to get out just the year. And then we use the plot tools to interactively set up our custom plot and then automatically generate the code I need to recreate that whenever I like. So now we need to start thinking about creating that mathematical model. Now really the whole goal of our model is we want to be able to make predictions in future situations where we don't already have the inputs, and we want to know, well, how good will those predictions be? So rather than waiting for future conditions to occur, what we're going to do today is we're going to take our data and we're going to split it up into two groups. One group we'll use to build our model to fit those coefficients. A different group will hold aside and basically pretend that it's future measurements and see how well does our model predict the solar ratio, compare that with the actual values. But in order to split the data up, I'm going to use something called logical indexing. That might sound a little complicated. It's actually a pretty simple idea. Let me demonstrate it with a simple example. So what I've created here is just a 5x5 matrix inside of MATLAB. MATLAB stores its data row first and then column. So if I want this value of 6 here, I can tell MATLAB go into the variable A, and then inside of parentheses tell it give me the third row, second column. It gives me a value of 6. I can also give it a series of numbers. So if I tell MATLAB go into the variable A, and then inside of square brackets give it a row of numbers, say 2, 4, give me the second and fourth row, and then using the colon operator, I can tell MATLAB give me everything along that dimension, so give me all the columns. So give me the second and fourth row, all the columns. So this is called subscripted indexing, and you can think of this sort of as specifying the location within your data that you want returned to you. But what if we don't know the location? What if we just want to do something based on a condition? So actually, let me recreate this in a format that's a little closer to what we're working with today. So here I've created just a one-dimensional list of numbers. This is 1 to 8 randomly permutated. And let's say I want to know where inside of this list is it less than 4, and I want to modify the values wherever that occurs. So in MATLAB, let's say I want to create a new variable called IDX that will tell me where that is. This is equal to wherever A is less than 4. And now you notice in the original variable A, at every location where that condition was true, in the result, it's a 1. Wherever that condition was false, it's a 0. This then allows us to specify what to do based on these locations where it's a 1, rather than specifying row and column. So here I'll tell MATLAB go into the variable A. Wherever IDX is true at that location, I want you to set that value equal to 0. Now you see all the locations in the original A that became a 1 are now set equal to 0. I could also use this to remove values. So if I tell MATLAB go into the variable A, and wherever A is greater than 5, for every location where that is true, I want you to set that equal to empty brackets, an empty matrix. And that tells MATLAB I want to completely remove the values at all these locations. So now I hit enter. You see all the values that were greater than 5 are now removed from my data set. So this is called logical indexing, and this is what we're going to use to specify which part of our data do we want to hold aside. And let's say we want to override the variable IDX here, and IDX is going to be true wherever the condition meets our criteria for what we want to hold aside. Now you may have a number of different ways that you might want to specify what do we want to hold aside, what do we want to use in our model. Today, for simplicity's sake, we're going to say we want to split this up based on the year. And I want to use, in my modeling, wherever the year is not equal to 2006. So we're going to hold the year 2006 as separate. Okay, so now we're ready to take the data we need for our model and split it up. So here I'm going to say my solar ratio is equal to solar Davis dot, and then again I can hit S and then hit tab and it will autocomplete, of wherever IDX is true. And let's say my relative humidity is equal to wherever solar Davis dot average relative humidity at IDX is true. Oh, and actually we got a little ahead of ourselves. Our formula requires the change in temperature for the day. We actually don't have that yet. So let me create it in a variable called del T. And this is going to be equal to wherever solar Davis dot max air temp minus solar Davis dot min air temp. And notice that I can do that just in one command. It will take every row in max, subtract the row in min, and store that in del T. So now I can segment it. Let's call this my del T. This is equal to wherever del T of IDX is true. Okay, so now you can see I have these three variables down here in my workspace, and you can see they have fewer rows. So we have less data now. We're just using the part that we want in our modeling. So now it's time to actually create that mathematical model. In order to do that, I'm going to come up to the Apps tab. Now, the idea of a MATLAB app was new in the 2012 beta release when we got this new desktop, but what they represent has been around for a long time, which is the different graphical applications that come with MATLAB and its various toolboxes to help you get your work done. You see a couple of them here, and if I expand this out, you'll notice that we actually have quite a few across our product line for different areas like computational biology, test and measurement, image processing, signal processing, controls, math. And I really like these apps because they allow you to very easily apply new ideas, new algorithms to your data before you even need to think about, well, what kind of functions do I need to call? What kind of syntax do I need to use? And for today, we're going to go up to the curve fitting app. So the curve fitting app comes to us from the curve fitting toolbox. If you're unfamiliar with the concept of toolboxes, these are add-on packages to base MATLAB that give you additional pre-built functions and examples and documentation, and in some cases, graphical applications. And the curve fitting toolbox is great for fitting equations of the form y is equal to f of x and z is equal to f of x and y. One of the things it gives us is this nice interactive environment. So I'm going to start up here on the top left and pick out my data from the workspace. Let's say temperature is my x, The relative humidity is my Y. Solar ratio is my Z. So I can pick this data out, and down here you can see the resulting cloud of data points. Up in the top, I can interactively pick out what kind of fit do I want to try. So maybe I want to try a polynomial first. And let's try degree 1 in X and Y. So here's a linear polynomial fit to our data. You can think of this as taking one big sheet of paper and trying to position this piece of paper so it best explains the behavior in our data. Over here on the left, you can see the results of the form of the equation, as well as the computed coefficients, confidence bounds, and some statistical measures for the goodness of fit. And one of the reasons that I really like this app is we didn't have to go looking for functions or syntax in order to create this. We can do all of this very easily. And if I want to increase, let's say, the number of degrees in these different variables, and let's try refitting it, I can do that very quickly and see, well, what's the result? But in our case, we know the equation that we want to fit to it. We have our own custom equation from back on that slide. So I can actually enter in my own custom equation, any equation that I can define in terms of X and Y. It could even be a call to a separate MATLAB function file. Now, just to save myself a few keystrokes, because I don't actually remember offhand exactly the form of that equation from the slide, I'm actually going to come up here to the File menu inside of the curve fitting tool, and I'm going to load a previous session. So we can save these sessions for later use, or we could actually pass them off to other people so they can open up and look at it. You see this .sfit file here. And so here it'll load in my previously saved session, and here you can see the custom equation that we're fitting. Here's the result of that fit. And over here on the left, you can see the results of fitting that equation. So these apps are great tools for very quickly and interactively applying a lot of new work to your data. There's a lot of additional tools here in this curve fitting app that we could try, but let's say this is good enough for today. So what I'd really like to get back from this is the ability to automatically refit this model, estimate those coefficients for any new set of data that I come across. So what I'm going to do, similar to what we've done a couple of times today, is go to the File menu, Generate Code. And MATLAB will give me a function that will refit this model for any new set of inputs. So here I'm going to save this file. Let's call it Create Fit. And down here we can call it. So this is going to be giving back a model that describes this fit. This is equal to the function Create Fit. And then my inputs, my del T, my relative humidity, and my solar ratio. This will refit the equation. It will give me back my model. And then if I open up this window, expand out the command window, you can see the actual model that I've created. So this model is actually an object in the object-oriented sense of the word. Now, if you don't understand object-oriented programming, don't let that scare you. You don't need to understand it to use MATLAB and be successful with it. You can think of it just as a container for everything we need to know about our model, so it's not just a series of numbers. And you see here, I printed out the form of our model and how we can use it. So we can actually use this model and give it some inputs. So model, and then del T. So let's say I want to estimate a 20-degree change in temperature with 80% humidity. And our model predicts in those conditions, we will have a solar ratio value of 0.519. But I don't want to predict for just those values. I want to predict for the entire year 2006 that we held out from our initial prediction. So down here, let's say I want to save that as prediction radiation. This is equal to our model. And then our input is del T. But which part of del T? So up here, IDX tells me where it's not 2006. So down here, what I'm going to do is I'm going to use the tilde operator to invert it, set ones to zeros and zeros to one. That will tell me where it is 2006. So del T and solar Davis dot average relative humidity of not IDX. And there we go. And that just ran it through our model and made predictions for the entire year 2006. If we want to then see the difference between that and the actual values, so that's our prediction error. This is equal to our solar Davis dot solar ratio of not IDX minus the prediction radiation. So now back here in our workspace, we can see these new values. If I want to see some ways to plot this, let's go to our plots tab and maybe try something like a stem plot. And so what you see here is what's called a stem plot, which shows the differences between our actual value, the solar ratio, minus the predicted value. So it's just one of the many ways that we might try to visualize this and try to understand how well our model is doing. So We could keep going with this analysis. There's a lot more that we could dig into here, but let's say that's good enough for today. And that pretty much takes us through our entire process, right? So we were able to import the data with the import tool, generate code to customize that, use the plots tab to very quickly generate lots of different plots, use the plot tools to customize it, and then generate code to automate that. We use logical indexing to segment our data, then use the curve fitting app to fit our custom equation to our data, and then automatically generate this function up here to capture that information. And then we were able to compare the prediction for 2006 with what actually happened. So that pretty much finishes the middle step in our data analysis workflow, explore and discover. Now we need to start thinking about how can I share this with other people. So the first thing I might want to do is take all the work that I did interactively in the command window and copy this over to a file so I can reuse it. So I could sit here and try to think about, well, what commands did I use, or if they're still there in the command window, maybe I could scroll back up and copy paste. But let me show you an easier way. So down here in the bottom left, I have a window I've had hidden so far called the command history. This is just a collection of all the commands that have been entered at MATLAB's command prompt, pretty much going back to the last time you cleared it. So this is great whenever you have those moments of, how in the world did I do that yesterday or a couple of weeks ago? Go back and look at your command history. It should be in there somewhere. So if I scroll up here, I can pick out just the files that were entered at the command prompt that I want to keep. So here, let's say I want to import my file, and I'm going to control click here, get our year, do our custom plot, and then do our logical indexing, create our model, make our predictions, and do a stem plot. So I can control click to grab just the ones I want, right click, and go to create script. And this will copy all those commands over into what we call a MATLAB script file. And a script file is a very simple idea. Basically, when we run this file, it runs all the commands in exactly the same way as if we had manually entered them all one by one at the command prompt. So now we have this. We can save this file. Let's call it my script. And now again, I can clear my workspace, clear my commands, so we're back where we started. And now that I have this file, I can go to my editor window and run it. Or you may notice in my current folder, now we've got this my script file here. I can just type it out, hit enter, and it will run all the commands in that script exactly as if I had entered them at the command prompt, and you can see we're right back where we were. So now I have this file, I can rerun it myself, I can hand it off to others to use, but it might not be too obvious what's going on here. So it's always a good idea to add comments to your code, just explaining what's going on. Not just for other people, but I also find it's a little scary how quickly I'll forget why I wrote my program the way that I did. So we can add comments in MATLAB using a % marker. You notice this turns the text green. That just tells MATLAB that this is just text explaining what's going on. And let's say that we want to explain that here this is import data from Excel spreadsheet. So that's the basic kind of commenting, but we have another type of commenting in MATLAB, which is the double % marker and the space. This creates what we call a section inside of our code. I'll create a few of these and then explain what they do. So that section, let's call that visualization. Down here, we'll call this whole thing modeling. And we'll add one more for completion up top. Let's call this import. Now, creating these sections has a couple of benefits associated with them. For starters, it's just a nice, quick, clean, easy way to make different parts of our program visually distinct. So we can see this is the section for import, this is the section for visualization, this is the section for modeling. We get bolded title line drawn across the background, changes color depending on where my cursor is. It also allows us to just run a certain part of our program at a time and not need to run the whole thing. So if I again clear my workspace, clear my commands, now I can use these commands up here in my editor window to run just a part of it. So run in advance will run the section my cursor is currently in, move the cursor to the next one. So there you see we imported the data. Now I can click it again to run visualizations, and click it again to run modeling. So this can be great to run just certain parts of my program at a time and not need to run the whole thing at once. The last big benefit of using these sections comes when we want to share this as a documented report. So now I'm going to come up to the Publish tab and just click Publish. And what this will do is this will run my MATLAB file and will capture everything about it. All of the code, all the comments, any figures that are generated, any plots that get sent to the command window, or any outputs to the command window. It automatically generates a documented report. So you see the sections inside of our code become the sections inside of our report. Regular comments populate the text. You can see actual commands, and as well as any output from MATLAB, including what was printed to the command window and also any plots. So this is a fantastic way to very quickly and easily go from the work you've done in MATLAB to a portable, readable document that shows exactly what you did and how you got the results. Now, if we go back to the Plots tab, you can see some additional options up here to help you customize it so it will plot as, let's say, bold or italic or include LaTeX or outside images. The only option I really want to point out right now is in this Edit Publishing options, and that's the output file format. So we can publish straight from a MATLAB script to an HTML report or XML, LaTeX, Word doc, PowerPoint, or PDF, whichever format is most useful to you. So I think you can see how we can work inside of MATLAB, going through those three phases, accessing our data, bringing it into MATLAB, plotting it and analyzing it and building up mathematical models, and then documenting it, sharing it as a report. And if we keep building this analysis up, we might eventually wind up with something like this file down here. So this is a pre-built file that we had already made. And you can see here we're including a lot of comments, so we're really doing a great job explaining what's going on. But you see it's the same basic idea with importing data and creating visualizations. And if we were to publish this, this is actually what created the HTML document that we saw way back at the beginning. So this was the document that we generated with one click of a button from that pre-built script that you just saw. Okay, so that's pretty much it for today. So let's go back to the slides and spend just a minute wrapping up. So there are a number of different ways that we could use MATLAB with Excel. So with just the base MATLAB package, we can pass data back and forth. We can read it in using, for example, the import tool. We can also do things programmatically, reading it in with XLS read, writing it back out with XLS write. But there are some more advanced options we did not have time to explore today. For example, we have something called Spreadsheet Link EX. This allows a running session of MATLAB in Excel to interactively pass data and commands back and forth. This is a great option if you find you typically have both programs open and you're developing in both at the same time. If you are developing applications in MATLAB for others to use who might not have MATLAB, then we also have an option called the Builder EX. So if we want to take what we've done in MATLAB and share it with others, what are our options? Well, if we have MATLAB and they have MATLAB, we can just give them our MATLAB files or MATLAB apps, and they can use them. But what if they don't have MATLAB? Well, we also have what we call the MATLAB compiler, which can take any MATLAB application and compile it as an standalone executable or C-shared library. We also have what we call the builders, for example, the Builder EX for building standalone Excel add-ins, or the builders for building things like Java objects, COM components, or .NET assemblies. So, how does this work? Well, step one, just build your application to the point where you're ready to share it. Then run it through the MATLAB compiler or maybe one of the builders, and out the side comes your component, whether that be an EXE or a C-shared library or an Excel add-in. And the process here is MATLAB takes all the MATLAB code that is necessary to run your application, pulls it together, and then puts a wrapper around it so it essentially becomes an EXE or an Excel add-in, but it just calls your MATLAB code. It then encrypts it so only the MATLAB engine can understand it. This component that you build is then freely distributable. There are no licensing restrictions, there are no royalties. You can give it away to whoever you want. If you have the commercial version of MATLAB compiler, you can even turn around and sell these components. And you can pass it off to whoever you like, but because they are actually running the MATLAB code under the hood, they do need access to the MATLAB runtime libraries, what we call the MATLAB compiler runtime or MCR. The MCR is also freely distributable. You can package it together with your application, or your end users can download it from our website at any time so they can run your applications without needing a copy of MATLAB on their machine. So there are many different benefits to using MATLAB. Here's just a few of the ones that I hope you saw today. There is an incredible amount of built-in functionality surrounding MATLAB. Plotting and visualizing data and customizing it is very, very simple. MATLAB has a lot of tools built into it to help you automate analysis routines, and it integrates with Excel and many other environments. So if you want to learn more, what should you do? Well, I encourage you to go to our website, mathworks.com. We have an incredible amount of resources there. In the top left of our website, if you go to Products and Services and then MATLAB, you'll come to this page here, the MATLAB product page. This summarizes a lot of our key resources surrounding MATLAB. On the left, I suggest you start with things like videos, code examples, and webinars, which are recorded presentations similar to what you're seeing today, or dive into documentation or a list of functions or some of the other resources on this webpage. In addition, there are many other useful areas of the website, such as pages for resources focused on different industries or application areas or focusing on academia. We also have our user community, what we call MATLAB Central. A number of useful parts for it. Areas like the file exchange, where users from all over the world can post tools that they've built in MATLAB for others to freely use. There are over 19,000 user submissions on the file exchange. There's also an area called MATLAB Answers, which is a free-to-use online Q&A forum for the MATLAB community. along with many other useful resources such as blogs by a number of developers around the company. Well, that's about all the time we have for today. Thank you all and have a good day.